Okay, good afternoon. Welcome back to math and modeling methods. Whoever didn't pick up their exam last time, I have it here. I finished to enjoy it. So, okay. So today we are going to continue our discussion on partial differential equations, and so far we've addressed partial differential equations in steady regime and transient regime, and we've mastered the separation of variables method and used that in combination with superposition to address issues with multiple heterogeneities or non-homogeneities. We see that it's an effective method. It's limited in the sense that you're still dealing with very simple problems. Okay, you're still dealing with problems in squares or rectangles. You're still dealing with linear problems where the conductivity has to be a constant, where the properties have to be a constant, density, specific heat. And the only thing that you can complicate is essentially the type of boundary condition. The first kind, where you impose temperature; second kind, where you impose a heat flux; or third kind, where you impose a convection coefficient. But anything other than that, even if you decide that one of the boundaries is a radiation boundary condition, boundary condition is inherently nonlinear. It's a temperature to the fourth power, and therefore that cannot be directly solved with the methods that we've actually used here, or any analytical method for that matter. So basically you have to rely on approximations and rely on linearizations of the equation and so on. Now, is that also happens when you have situations where, for example, the boundary conditions might be space dependent. Okay, they're not necessarily nonlinear, but let's say I give you a flux that changes on a boundary as a function of position. Yeah, you can address that because it requires you to integrate it somehow. At the end of the day, once you impose that condition, it's going to come out inside of an integral. But how about if that integral doesn't have a closed form solution? Then you still be approximating. You still need to rely on some quadrature or numerical approximation of that integral. So why don't just go back to the equations and say, well, let me start from scratch and try to approximate the solution of that equation, which is what we did with ordinary differential equations. We found many analytical techniques to address them, but then we say, well, the heck with it. Let's just start from scratch and do them using either Runge-Kutta or Euler's method or whatever. Okay, now the same thing we can do with partial differential equations. However, there's a gamut of techniques to address partial differential equations numerically. The oldest of these techniques is the finite difference method, where the differentials and the governing equation and boundary conditions are approximated using Taylor series approximation. Just finite differencing. Okay, you're all familiar with that. You've seen them. You've used them in many instances, and all we have to do is adapt it to this particular set of equations that we have. But that's the oldest method. That method is actually, I would say, almost 100 years old. It dates back from the 1920s. The end of the First War, they had some issues in resolving some problems, and then it predated computers, so these things were approximated by hand. Later on, there's other techniques that caught on and others that didn't caught on or didn't catch up. Such like, for example, the finite element methods, which is one that you see on a daily basis when you use modeling packages. Any structural package out there, ANSYS or even the solver within CATIA or SolidWorks, whichever one you use, has a finite element engine, which is essentially a conversion of differential equations to algebraic analogs. So basically, you take a set of complicated equations and translate that into a large set of simultaneous, very simple equations. That's what all numerical methods do. That was back in the 60s when finite elements was developed, and in the 70s and 80s they developed something called finite volumes. Finite volumes is what every CFD package has. However, there's some obscure CFD packages that use finite elements, but those are just for academic purposes. So all the serious ones use finite volume method. That's completely different from finite element, has nothing to do with that. It's still a numerical method that takes differential equations and turns them into algebraic analogs. And then the boundary element method also around the same time, and that was developed further for, it's very advantageous for other techniques, for other problems. And lately more meshless and spectral methods are some techniques of choice. Some of these techniques we're going to cover in more detail on the follow-up class to this one, which is going to be heavily concentrated on modeling, none of the math. Well, obviously it'll be math, but the math is underlying the numerical methods implementation. And what we're going to do in this class is just introduce finite differencing as a way of solving partial differential equations. Okay? So, and modeling methods. And this is lecture, remind me, 22? Lecture number 22, yes. All right, so all the way up here, so we're going to talk about the finite difference or differences method. Some people call it finite differencing or finite differences. In any case, it's just FDM. For the approximation of solutions of PDEs. Well, as a matter of fact, it needs to be initial value problems or boundary value problems. Okay, we need to have a well-posed problem, not just a PDE. We cannot approximate a general solution to a PDE. We need to have boundary conditions, and we need to have initial conditions if the problem is an initial value problem. So the only thing we can hope for is to approximate particular solutions. And at the end of the day, we're not going to approximate the solution in functional form like what we do with analytical techniques, so we have a series representation of the solution. What we hope for is to represent or approximate a solution discretely. Are discrete either set of points or set of meshes or over a spectral kind of volume or whatever it is, it's just a discrete representation of the solution. So recall the Taylor series approximation of first derivative, the phi dt. So if we have a function phi of which we need to calculate the derivative in time, for example, it can be done in space, but let's say we need it in time. So then we discretize time as a set of discrete points in time, separated by steps delta t, such that n goes from 0 to some final value n. So we have an n number of time steps. So this is n time steps of size delta t. So that means discretizing the time scale so that the time variable goes from 0 to some final time. So then we can say that through Taylor series approximation, we already did this demonstration of how we end up with, for example, we want to know the derivative d phi dt at some time n, or some value of time n. That would be phi at n minus phi at n minus 1 divided by delta t. It's a very simple approximation that relies on discrete values of phi in time. If we have phi at time n and we have phi at a previous time step, we subtract the two divided by the size of the time step, and that is an approximation. That is actually an approximation of the first derivative. And this is order delta t accurate. This is what's called first order accurate. So the smaller you make delta t, the better the expected error linearly with delta t. If you shrink delta t in half, you expect the error to be cut in half. That's what delta t accurate means. And this is called a backward difference approximation. backward difference approximation. It's backward because in order to approximate the derivative of the function phi at the current time, you need the solution or the value of phi at the current time and the previous time. So you're going backwards in time to be able to calculate the solution now, or to calculate the derivative now. Also, you can do it as the phi dt at n is approximately phi at n plus 1 minus phi at n divided by delta t. This is also order delta t accurate. And this is called forward difference approximation. Okay? Or you can do d phi dt at n is approximately phi at n plus 1 minus phi at n minus 1 divided by twice delta t. So notice now we're going forward and backwards in time. And when we did the approximation of these, we found that this, the truncation error, is of the order delta t squared. So these has to be order delta t squared accurate. That means that, that doesn't mean that the error is exactly predictable, because otherwise this will be an exact problem, an exact method. We know that the error is bounded by delta t squared, and in the case of delta t squared, if you shrink delta t or cut delta t in half, the expected error is supposed to be a quarter or a half squared. And this is called central difference approximation. Okay, so why don't we always use central differencing when approximating solutions numerically? It's more accurate. If the level of effort is the same, we're not doing additional computations. Well, there are some issues with stability. There are some issues also with applicability. Sometimes we cannot apply it because we don't know what's going on in the future. We might know what's going on in the past. It's called causality. In time scale, in space scale, you don't have causality, but in time you have causality. Everything happens because of a cause. Okay, so there's only certain directions that you can take in time. And also, it has to do with other things that will become obvious in our next few slides here. All right, now these approximations can also be implemented in space. Say, for example, we let another discretization, but now this discretization is going to be space discretization. We let xi be equal to I times delta x, such that I goes from 0 all the way to big I. That will make I space steps of size delta x, which if you see is equal to some L divided by I, such that x goes from 0 to L. Okay, so we can discretize the space like that. So let's say that the coordinate x is bounded in this problem that we're trying to solve between 0 and L. We can break it up into I spaces, space steps, and each of size delta x. So the central, this is called the space discretization. Space discretization. The previous one was the time discretization. So the central differencing, the central difference approximation is the phi dx at point I, and let's say time n. Now we have two things to worry about, space and time, and we have two discretization, I representing space, n representing time, would be, well, what's going on with the variable right of point I at the same time level? What is the value of the variable left of point I? Now divided by 2 delta x. And as you can expect, this is order delta x squared accurate. All right. Similarly, and you can do this is a central differencing approximation. You can also do this backward differencing and the forward differencing the same way we did it on the previous slide. Now, sometimes, well, it's obviously better to apply central differencing, again, because it's more accurate, or the error decays faster. But if you're on the boundary, you cannot apply central differencing, because then you'll be looking at points left of the boundary, left of the left boundary, which don't exist. They're not part of the domain. So on the left side of the boundary, you need to do forward differencing. And on the right side of the boundary, you need to do backward differencing. You understand? So that's why you have to rely on an approximation that is less accurate than another, and combine them. So similarly, the central differencing approximation of the second derivative becomes, well, and by the way, again, this is an approximation, so, and let's say at time n, point I, this becomes the value of phi to the right of point I minus twice the value of phi at the same point I plus the value of phi to the left of point I divided by delta x squared. And this is also delta x squared accurate. Additional either forward differencing approximation and backward differencing approximation of higher derivatives, higher order derivatives may be easily formulated. But with what I've shown you here, it's already enough for us to formulate an approximation of the types of problems that we've been dealing with. What are the types of problems that we've been dealing with so far in terms of PDA, partial differential equations? Diffusion problems, right? When we have the Laplace in space and we have first derivative in time. Or wave-like problems where we have Laplace in space and second derivative in time. Okay? Either of those, we can deal with what we have, with these approximations. Okay, all we need to do is formalize it, make sure we do the correct bookkeeping to keep track of the discretization in space and time, and off we go. So, for instance, for example, the 1D heat diffusion equation let's say I'm going to make it constant coefficient, constant conductivity. Although it's not necessary now that we're dealing with a numerical method. If it's a numerical method, we can make the conductivity change whichever way we want to, and all we have to do is account it for properly. We can even make, we can put in a generation term, but let's keep it easy. Sorry, this is time. Let's keep it easy like this because we can have an analytical solution, right? And then if we have an analytical solution, we can compare it to the one that we're going to produce numerically. At least find a residual and see how well our numerical approximation is performing. So basically, this is quantifying, or could quantify, the heat conduction time of a 1D space, which can be a 2 or 3D space that is effectively insulated in all directions but the longitudinal direction. So we have x equals 0 to L, and something's going on along that direction. There's conduction, and there's also diffusion, so things change in time. Remember, our space is going to be belong to the interval between 0 and L, while our time is going to belong to an interval between 0 and TF. Okay, well, that's not true for time. Time doesn't have a bound, doesn't have an upper bound, but that's the region of interest for us. Okay, we have to stop it somewhere because the numerical approximation cannot go forever. So we're going to say I am only interested in to see what's going on with the temperature within the domain 0 to L, and in time from start all the way to some final time that I set arbitrarily where I would imagine things will start settling down, for example. So now we're going to let xi be equal again to I times delta x, such that I goes from 0 all the way to I, and delta x is equal to L divided by I. And Tn is equal to n times delta t times step size, where n goes from 0 to n, such that delta t is equal to the final time of interest divided by n. That's a discretization. So, if I were to map space to time, let's say that this is the arrow of time, starts at 0 right here, and let's say that this is the arrow of space. We have I plus 1, we have I minus 1. This is I equals 0, I equal 1. This will be I equal capital I, and this will be I equal capital I minus 1. And this will correspond to the time level equals Tn. And then we'll have the same discretization and this will be T equals Tn plus 1 at the next time level. The size right here is delta T. The size right here is delta X. Again, this is I plus 1, I minus 1, 1, I equal 1, I equal 0, I equal I minus 1, and I equal I. All right. So, what I'm going to do is I'm going to take that differential equation and that discretization, and I'm going to use central differencing. I'm going to abbreviate a central differencing approximation in space. This is a C. And forward differencing approximation in time. Okay, so I'm going to take this equation right here, and if I do central differencing approximation in space, I am going to have t at I plus 1 n minus 2t at I n plus t at I minus 1 n divided by delta x squared is equal to 1 over alpha, and I'm going to use a forward differencing approximation for this one. T at n plus 1, I, t at n, divided by delta t. That is the algebraic analog, or the discretized version of the PDE. This is discretized PDE. Alright? So then I'm going to solve for the temperature at the next time level. T at I n plus 1 is equal to T at I n plus alpha delta T divided by delta x squared of Ti plus 1 at n minus Ti at n plus Ti minus 1 at n. And this is called an explicit FDM, finite differencing method scheme. It is kind of obvious why it's called explicit. It's because we can explicitly know the solution at any point in the future by knowing what goes on in the past. Okay? So if we know the temperature distribution at every point I, including I plus 1, I minus 1, I, every one of the points at any time level n, let's say at n equals 0, that's the initial condition, and normally you know the initial condition, right? You need to know the initial condition for the problem to be well posed. So if you know the initial condition, you start at n equals 0, you know the temperature everywhere, you plug the temperature here for every point I, then you know the answer at the next time level. That's all it takes. All you need is a little loop to get you to the temperature of the next time level. Then you sweep all points I, so that you can actually find out what the temperature is at every point in space for the next time level. And then you advance time one step. And then you'll do it for n equal 2, and for n equal 3, and so on and so forth. So it's an explicit scheme. You don't need to solve matrices or anything like that. You pick a point I, you get the temperature based on whatever the temperature was in the past. Okay, so solution at point xi at new time level n plus 1 depends only on the solution at previous time level n. Okay? So that would mean that if you take the discretization again, and I'm going to draw a line here, I'm going to draw a line here representing space. Again, this will be I equals 0, I equal 1, I plus 1, I minus 1. This will be I equal big I equal I minus 1. This will be I equal, I'm going to do it on this side, I equal I equal I minus 1. I equal 0, I equal 1. This will be I plus 1, and I minus 1. Any generic point, and this corresponds to T n plus 1, and this corresponds to Tn. So the solution here will depend on the solution on those 3 points on the previous time level.
I have a question.
Mm-hmm.
Are you assuming the edges to be constant, like at I equals 0, or you can't get the previous point?
Yeah, you can. Yeah, that's right. So this you've identified the fact that these formula here will not apply to I equals 0, right? Mm-hmm. Because then it will actually reference point minus 1, which doesn't exist. It also doesn't apply to point big I, because it will actually address or reference point big I plus 1, which doesn't exist. It's outside the domain. So we need to do something about the edges. Okay? We haven't addressed that yet.
Okay.
So this scheme is valid or I equal 1 to I minus 1. Every node, excluding the endnotes. Okay? All right, so what do we do at the endnotes? At endnotes, we apply boundary conditions, right? The governing equation, we apply that inner node. On the endnotes, we apply boundary conditions. So at endnotes, that would be I equals 0 and I equal I. We must apply boundary conditions. BCs. All right, now we have alternatives. First kind, so let's say at I equals 0 or I equal I, and let's say first kind. The first kind boundary condition, when we call also Dirichlet or forced condition. What we say in first kind boundary conditions is that the Ti, the actual representation will be X boundary is equal to some T boundary. Okay? It is where X boundary is either 0 or L, such that X boundary is equal to 0 or L. So that would mean that T at I, comma N, or actually N plus 1, because we're trying to advance in time, is equal to that particular T boundary. So if on the left-hand side or on the right-hand side, there's a first kind boundary condition with the temperature supplied, that's all we need to do about that end node. Ti at N plus 1 is equal to that temperature that is imposed. Second kind is also called Neumann or natural, in which case we say that Q, the normal flux at the boundary, is equal to some Q boundary. That means that minus K dt dN times on the boundary is equal to Q boundary. Now we use a forward differencing approximation of the Tdx at I equals 0, or backward differencing approximation of the Tdx at I equal I. And then that will result in Ti at N plus 1 is equal to Ti plus 1 or Ti minus 1 at N plus 1 minus delta X QB divided by K. All right, it will be I plus 1 if we're node 0, or I minus 1 if we're not node I, the final. So what we're basically saying is that this dt dn, which is simply dt dx times the normal vector, either negative on the x or positive on the right hand side, negative on the left, or positive on the right hand side. The dt dx is approximated by ti minus ti minus 1 divided by delta x when you're on the last node, or ti minus ti plus 1 divided by delta x when you're in the first node. Either way, it comes out to be the same. Third kind. This is called Robin or convective. And this basically says that Qn and on the boundary, whichever side of the boundary is equal to some film coefficient h times d on the boundary minus some t infinity. So that means that minus k dt dn on the boundary is equal to h times t along the boundary minus t infinity. Again, use a forward differencing approximation of dt dx at I equals 0, or backward differencing approximation of dt dx at I equal I on the right side node. And what we'll end up with is ti at n plus 1 is equal to ti plus 1 or I minus 1, depending on whether you are on the last node or the first node, plus the BO number times t infinity divided by 1 plus the BO number. Such that this is equal to h times delta x divided by k, or BO number. BO number is just a ratio of convection to conduction, what dominates over what. Alright, so that's how we deal with boundary conditions. We first apply the internal scheme, this one, at every node from 1 to I minus 1. All the internal nodes, you exclude the end nodes. And that means that you'll be explicitly calculating the values of all temperatures at the next time level and all internal nodes. Once you have those, then you can implement this boundary conditions. Whether you have first kind, second kind, or third kind, you apply, well, if you know the temperature, that's the easiest one. If you know the flux, then you do this. On the first node, you use I plus 1, and on the last node, you use I minus 1. And if you have third kind of convection, you apply this condition right here. Knowing that, you already know Ti plus 1 or Ti minus 1 at the next time level, n plus 1. Alright? And that is surprisingly easy to implement. I'll show you in a MathCAD spreadsheet in a minute. Okay? So whatever we did to do the eigenvalue expansion and the series expansion, apply orthogonality to calculate the constants of integration and the eigenvalues and so on, to end up with a series expression for the continuous form of the solution, can all be replaced by these numerical approximations. Is the numerical approximation good? Well, it's left to be seen. There's obviously truncation because we're using finite differencing approximation. That's why we call it FDA or BDA or central differencing. These are approximations of the derivatives, and therefore there's truncation. Can we control the truncation? Well, make delta x tiny. Make delta t tiny. Okay? Well, that's not necessarily that straightforward. So the solution is or the solution process is started at time t equals 0. The first time step where the initial condition is known. That means t is can be some function of x, and therefore all the values of t at all nodes I and n are equal to f of xi for I equals 0 all the way to I and n equals 0. And advanced in time explicitly. So, can the approximation be perfectly accurate if delta x and delta time tend to 0? You would think so, right? Because the truncation error in space and time depend on the size of delta x and delta t. However, that's not possible for many reasons. It's not possible for us to take delta x and delta t to tiny, tiny, tiny value. Well, first of all, there's round off on the computer. Okay, the computer can only recognize differences between numbers that are so small. And second of all, there's stability. Okay, not possible because of 1, round off. Okay, the round off is smallest number or difference that the computer can recognize. Remember that computer, in order to represent real numbers with a fractional part, uses a floating point approximation of that number in a finite number of bits. Okay? If you're using double precision representation, which is kind of the standard, you're talking about 32 bits to represent the number. Okay? The first bit is actually reserved for the sign. 1 if it's negative, 0 if it's positive. The other 31 bits for the fractional portion and the floating point of that fractional portion. Okay? So there's a finite amount of spaces that you have to represent the number, and therefore 0 is actually not 0. 0 is just the smallest number that you can represent in a double precision string of 4 bytes, or 32 bits. And that is 10 to the minus, the round off in double precision is about 10 to the minus 16. That's the smallest number you can represent. But the most important reason here is stability. That is, the term is called the Fourier number must be kept below 0.5. So the Fourier number needs to be less than 0.5 for this explicit scheme to be stable. Otherwise, it will just oscillate to divergence. Okay, and the oscillation will be uncontrollable. Even if you make delta t tiny, delta x tiny, that number, which appears right there, as you can see, is the ratio of the time representation and the space representation multiplied times the diffusion coefficient. Remember the units of the diffusion coefficient? Meters squared per second? That cancels out delta t and delta x squared, so this is a non-dimensional quantity, right? And that non-dimensional quantity actually represents the ability for passing information through the cell in space and through the time levels in time. Okay? If that number is larger than 0.5, an explicit scheme will blow up. No matter what you do, it will blow up. Okay? Even if it's force, we use force temperatures on the left and on the right, it will just diverge to infinity. So that number needs to be kept below 0.5. The reasons for these? Well, we need to do what's called a Fourier analysis, which is impose a wave on the grid and try to propagate it in time, and you will see that at the limit, when FO is equal to 0.5, the propagation of that wave becomes unstable. Okay. It's actually quite simple, but it's something that is beyond the scope of what we're trying to do here. All right. Now, all of these was based on using central differencing in space and backward differencing in time. I'm sorry, central differencing in space and forward differencing in time. What if we had used the opposite? What if we had used central differencing in space, let's keep it that way, and then we use backward differencing in time? The order of the approximation is the same, right? We're still talking about order delta t accurate in time. Forward or backward differencing is still order delta t accurate. So, what if we use backward differencing approximation in time and central differencing approximation in space to discretize? Again, we're dealing with a 1D diffusion equation, heat diffusion equation. So if we do that, the central differencing in time will become Ti plus 1 at n plus 1 minus 2 Ti at n plus 1 plus Ti at n plus 1. All of these divided by delta x squared is equal to 1 over alpha Ti at n plus 1 minus Ti at n divided by delta t. Notice the difference now? Stuff on the left hand side is now evaluated at the future time level where we don't know the solution. Right? Again, let FO be equal to alpha delta t divided by delta x squared. And this will become minus FO t at I plus 1, n plus 1, plus 2FO plus 1 Ti at n plus 1 minus FO at Ti minus 1 n plus 1 is equal to Ti at n. This is an implicit FDM scheme. That means that in order to know the solution at the next time level, you need other solutions at the next time level. In order to know what t at I, at point I, at the next time level, you also need to know what's going on to the left of it and to the right of it on the next time level, which you don't know. So that's why it's called an implicit scheme. You need to formulate this as simultaneous equations. So this will result in a matrix system. Solution on the new time level, n plus 1, depends on solution solution in the vicinity of xi at the new time level, n plus 1, and the solution at xi at the current time level n. So basically, I'm going to do it like this. This is I, this is I plus 1, this is I minus 1. Again, you're talking about Tn plus 1, the new time level. And this one is I plus 1, I minus 1. So we're interested in knowing this. In order to be able to know this, we need to know this one and this one. And that's related to the value of the temperature at point I at the previous time level. All right, these scheme will lead to a system of simultaneous equations when the expression above is evaluated for I equals 1 to I minus 1 at the inner nodes. Again, the expression does not apply to the end nodes. So we end up with minus Fourier at t0 at n plus 1 plus 2 Fourier plus 1 t1 at n plus 1 minus Fourier at t2 at n plus 1 is equal to t1 at n, which we know. Because from the previous time level, we know everything, starting from the initial condition. Then, minus Fourier at t1, tn plus 1, plus 2 Fourier plus 1, t2 at n plus 1, minus Fourier t3 at n plus 1 is equal to t2 at n, which we know. And eventually, minus Fourier t at big I minus 2, n plus 1, plus 2 Fourier plus 1, ti minus 1 at n plus 1, minus Fourier at ti at n plus 1 is equal to ti minus 1 at n. And we know this one. At nodes I equals 0 and I equal I, we can formulate similar expressions for the boundary conditions as we did in the explicit scheme. The way to implement the boundary conditions, identical to the way it's implemented in the explicit scheme. So eventually, leading to a coefficient matrix times T is equal to B. And that vector B contains, well, temperatures at the previous time levels, or information about the boundary conditions in the first entry and in the last entry. This is a linear system of equations. Now, what do we do with this linear system of equations? The coefficient matrix A is known, right? It's a combination of these Fourier numbers and these coefficients and whatever. On the first row, we're going to have information about the boundary condition on the left. On the last row, we'll have information about the boundary condition on the right. This right-hand side vector is completely known. It has the temperature at the previous times levels. And it has information about boundary condition on the left and boundary condition on the right, on the first entry and the last entry. So it's a perfectly well-posed linear system that we solve using any solution method. May be solved using any algebraic solution method, like Gaussian elimination, what else? What else can we use to solve linear systems like this? LU decomposition. Many methods out there, those are all available. Okay? SV decomposition, Gauss-Seidel, conjugate gradient, etc. These last two are approximate methods. Okay? Now, one thing to notice about this system right here is that, notice, we are trying to solve that system at every time step. Right? And so we do it for n equal 1, for n equal 2, n equal 3 to solve for the temperature at every time. Is the matrix changing at any time step? The coefficients of that matrix depend on the Fourier number and depends on the coefficients of the boundary conditions, which actually don't change in time. What changes in time is this right-hand side vector, because that contains information about the temperature at every time step, at the current time step. So this matrix here, we don't have to solve it every time. Okay? We can decompose it once and then evaluate it in the next time step. Well, we can invert it, which is essentially the same. Notice that A does not change along the time progression. Therefore, AX or AT is equal to B can actually be done this way. And the inversion can be done again through LU decomposition or whatever one of these methods that we use, but it only has to be done once. So inversion of A only needs to be performed once. All right. What else do you notice about this matrix? Okay, that's a good thing because inversion is a very, very time-consuming process. If you have 1,000 points in space, the matrix is 1,000 by 1,000. That would take 1,000 times 1,000 times 1,000 NQ floating point operations. That's 1 billion floating point operations, which in today's computers that will happen in a second, right? But if you had 10,000 points, Right? Now you're talking about 10 to the 4 to the power of 3, that's 10 to the 12, that's a trillion floating point operations, right? Now you need a petaflop to be able to solve for that. Okay, you need a cluster to be able to solve for that system in a reasonable amount of time. So we only have to do it once. But another particularity about this matrix is notice this system right here. The first row of the system of the matrix A has the first entry, the second entry, and the third entry. Everything else is 0. The second row has a coefficient multiplying the second entry, the third entry, and the fourth entry. Everything else is 0. Okay? So this matrix is actually quite sparse. It has a bunch of zeros, and then it has non-zeros along the diagonal, the upper diagonal, and the lower diagonal. Okay? Up diagonal and sub-diagonal. So, also, the matrix A is tridiagonal. Highly sparse. Okay? So the matrix A looks like this. The diagonal has numbers. A00, A11, so on and so forth. The superdiagonal and the subdiagonal have numbers. Everything else is a 0. There are very efficient techniques to invert these types of matrices, such as the Thomas algorithm. Okay, now why go through the, here's the question. Why go through the trouble of formulating an implicit scheme when we have an explicit scheme? And they're both the same level of accuracy, okay? Because they both use order delta t accurate in time, order delta x squared accurate in space. So the level of accuracy is the same for implicit and explicit. Explicit is pretty straightforward to implement. Implicit requires that matrix, and it requires the inversion of that matrix, and then it needs that to progress in time. It's highly more complicated to implement. The only reason why it is advantageous to use an implicit scheme, the only advantage of the implicit scheme over the explicit scheme is that it is unconditionally stable. The Fourier number doesn't need to be anything. You can make Fourier number 10,000. You can make that, remember the Fourier number? Alpha delta t over delta x squared. See what happens with the denominator of and be as high as needed. The delta x is what really controls the size of the Fourier number. For the explicit scheme, that number needs to be less than 0.5. Okay? So if you use a delta x, a space discretization that is too resolved, too small spacing between nodes, then the Fourier number is going to grow large because the denominator of the Fourier number has the square of the delta x. And then you're going to need to move to an implicit scheme because you're not going to get an answer. Unless you make delta t super slow, super small. Okay? So for every resolution you increase, for every step in resolution that you increase in space, you need to increase square of that in time. Okay, so if you cut the number of the points in space by half, or by double, if you double the number of points in space, that means doubling the resolution. then you need to cut the size of delta t by a quarter to maintain stability in explicit schemes, right? Otherwise, solution will blow up. So if we make delta t very small, then it will take a long time to actually reach steady state. Okay, you need to do a lot more time steps to get to the answer. All right. So this is explicit, fully explicit, and fully implicit. So additional mixed implicit schemes, for example, one that's well known is the Crank-Nicholson scheme, which is 50-50, is half implicit and half explicit, may be formulated for accuracy and stability purposes. All right. Now, can we formulate a finite differencing approximation for a steady problem? Notice that we started with transient, which is supposed to be the hard problems, so they depend also on time. Can we do this for steady problems? Yes, we can, but it will be a lot more complicated actually to do it for steady problems. Okay, we need to formulate an interpolation that works in space, okay, that ties up the boundary conditions on all sides. Okay, we're talking about partial differential equations, so we're talking about a 2D problem at least. We need to discretize x, we need to discretize y. We need to tie up the boundary conditions and the governing equation all in once in the same matrix. We're going to have a matrix that is fully populated with, it's going to be sparse, we're going to have zeros, but it's going to have dominant sections, and then you need to solve that system of equation. So a formulation of a steady problem is actually quite more difficult. However, you can use this transient formulation, explicit or implicit, and advance it in time enough so that you reach steady state. So let's say I give you a steady problem. What do? You invent an alpha, you invent a dt on the right-hand side, right? You progress it in time, in artificial time, respecting stability criterion, until you get to a point where the solution doesn't change anymore. When the solution doesn't change anymore, that dt on the right-hand side has gone away. And you've effectively achieved or reached a steady solution. All right? So, FDM schemes for steady problems may also be formulated. However, it is far more convenient to treat steady problems as pseudo transient problems. That means with an arbitrary diffusivity alpha and advance them in artificial time until a steady solution is reached. That's far more convenient than the alternative. So you can do this with steady state, and I can show you the notes. I have prepared a lecture for that, but it's only confusing. Okay. All right, so in the next 5 minutes, I'm going to show you an example real quick, and I'm going to give you some, I'm going to give you a spreadsheet that you're going to have available to work on the assignment, which I've already posted. Okay, the assignment has some analytical problems that you have to solve by series expansions, and then you have to do the numerical scheme. So, example. Let's say we have the governing equation, d second t dx squared is equal to 1 over alpha dt dt. Again, no generation, constant conductivity, that's fine because we have an analytical solution. Initial condition, t at x comma 0 is equal to f of x. And boundary conditions, we have q at x equals 0. That means that dt dx at x equals 0 is equal to 0. And then we have q at x equal L is equal to h times t at x equal L minus t infinity, which will make 0 for this example. That means that dt dx at x equal L plus h t at x equal L is equal to 0, such that h is equal to big H over K. We did this problem in class. So the solution is t of x and t is equal to the summation from n equal 1 to infinity Cn cosine of lambda nx e to the minus alpha lambda n squared t. That's the solution. Such that the eigenvalues satisfy this relationship. So those are the kind of the implicit eigenvalues. And Cn is equal to twice h squared plus lambda n squared divided by L h squared plus lambda n squared plus h times the integral from 0 to L of f of x cosine lambda nx dx. So we actually solved this problem in class. Now we're going to implement it. We have 2 minutes to implement it, but it's going to be that simple. All right. So let me go to the PC. I'll bring back this slide in a second. You'll see that same expression on the PC. Ready? So remote. Disappears. All right. It'll be much easier if we have MathCAD on every computer. But. Okay. All right. So here's the analytical solution. Okay, I'm making f of x a parabola. F of x, remember, is the initial condition. Okay, and for some reason, I can make it whatever I want, but for some reason I made it a parabola that's 0 at x equals 0, 0 at x equals L, and it's 100 at the center. Okay, the perfect center parabola. I'm making L equal 1, the length, conductivity equal 1, and diffusivity equals 10 to the minus 3. Okay, thermal diffusivity diffusivity for whatever material this is being conducted, or in which this is being conducted. Q0, I'm making 0. So the flux on the left, I'm making 0. The film coefficient or heat transfer coefficient H, I'm making it 1. And T infinity, I'm making 0. Okay? This is the loop that I use to determine the eigenvalues. Okay? Don't worry about that loop. It's just an expression that I came up with to actually solve that implicit equation for the eigenvalues. The tangent, tangent, what is it? Tangent of lambda NL is equal to H over lambda N. So I'm finding the roots of that equation through this expression. Okay? And I'm doing 100 of them. I think with 100 eigenvalues, making infinity equal to 100, that should be enough. So I have basically an array here with 100 eigenvalues. Notice that they are it's a periodic expression, but it's not uniformly spaced. That's what we found for these implicit relationships. The constant of integration for the series expansion is what I wrote on the paper. Okay, that includes the integral of the initial condition times the eigenfunction, and this is a series expansion of that for the representation of the temperature in space and time. Okay, notice that I make infinity in this case equal to 100. All right. Now up to onto the explicit representation. This is all that it takes to do this explicitly. Here I'm making the final time 1,000, so I'm only interested in knowing what happens after 1,000 seconds and during 1,000 seconds. I'm making, I'm using 10 nodes, so delta x is 0.1. Remember the length is equal to 1. I'm discretizing space, discretizing time. I'm going to discretize time with 1,000 time steps so that the time step size is equal to 1. I can change that. And that will lead to a Fourier number of 0.1. 0.1 is okay, because it's below 0.5. We're going to try with a number that gives us more than 0.5 and see what happens. The BO number, 0.1. This is basically the loop that controls time. This is the loop that controls space. Okay, the loop that controls time goes from 0 to n minus 1 as a progression of time explicitly. And the loop that controls space, the inner nodes between I equal 1 to I minus 1, and then the ones that deal with the boundary conditions. On the left, we have second kind boundary condition by Q0, and on the right, we have third kind boundary condition by T infinity. That's the same thing we wrote on the paper, on the slides. So what does that lead to? Well, I did it implicitly. I form a coefficient matrix A. I inverted that coefficient matrix A. I didn't use any special techniques to invert that coefficient matrix, but if I show you the coefficient matrix, you'll notice that it's tridiagonal. There's a bunch of zeros everywhere except on the diagonal, and the subdiagonal and the upper diagonal. See? So there are more efficient techniques to be able to solve this expression or to invert this matrix. But this is a routine that does the implicit solution. Slightly different, but we need the inverse of the matrix C here. All right, this is what we get at time equals 0. Right, the perfect parabola. Obviously, the explicit and implicit are perfect because we impose that as an initial condition. This is what we get after 100th of the final time, 0.01 of the final time. Okay, that's after 10 seconds, essentially. Notice that the solutions, both explicit and implicit, are over-predicting the exact solution. This is what happens after 10% of the final time. That's after 100 seconds. Now they're over-predicting, still over-predicting, and then it catches up. Then they catch up. At final time, they catch up. Now this is not steady state yet. What would be the steady state solution of this problem? A problem where we have 0 flux on the left and 0 convection on the right. What is the final solution of that problem? 0 everywhere. Okay? If the boundary conditions are not driving the problem, they're driving it down from an initial condition, but they're actually settling it to 0 perfectly. So at the end of the day, those two lines should go down to 0. That's a time equal to infinity, but it's left to be seen what infinity means. Now, if I were to make, let's say, delta x, I'm going to make it slightly smaller. Well, that should give me a better solution, still respecting stability. I go down, I get better solution, see? Better approximation. But now I'm going to double again the number of points in space. What happens to Fourier number? This actually says that there's a floating point error. It went to infinity. Okay? I'm not going to exaggerate. I'm going to make it 25 and see if I can get an answer. See, slightly over 0.5. So I should get something that where it starts to oscillate. See? See those oscillations of the explicit solution? Those oscillations just got worse. They actually get worse. They get so bad that you cannot see them after 10 seconds. See? You cannot see what's going on here. The blue line doesn't even show up. That's over the limit of stability, so the answer doesn't even apply. All right? So this is it. I'm going to post this spreadsheet for you to see, and you can reuse it as you see fit, especially for the homework assignments. We'll talk about those on Thursday. Okay? Thank you for your attention.